We'll talk about mixtures of gases. Many gases are not just a pure compound or element, they're actually mixtures. And we have a nice mixture of gases in the classroom. We call it air. Air is good. We like air. The interesting thing about gases, kinetic molecular theory predicts that each component in a gas mixture acts independently of the other gases in that mixture. And if we think about how there's really no attraction between gases under ideal conditions, between the particles, that makes sense. If all the gas particles are acting completely independently of each other, does it really matter what they are? No, it doesn't. So if you have oxygen and nitrogen together in a container, they're each going to act like they're the only gas present. The pressure, there's going to be a pressure because gases exert pressures on their environment, on their containers. The pressure of each individual component will be the same whether it's by itself or not. And the total pressure of the mixture will be the sum of all those individual pressures. Better read this slide. So the pressure that one component of a gas mixture exerts is called a partial pressure. So say you have a gas mixture of gas A and gas B. Gas A is exerting a pressure and gas B is exerting a pressure. And the pressure that each of them exerts is called the partial pressure. The total pressure of the mixture would be the combined partial pressures of all the gases. And the partial pressure of the component is related to the fractional composition. So if you have equal amounts of gas A and B, their partial pressures are going to be equal. If 75% of the gas is gas A, then 75% of the total pressure is going to be from gas A, and 25% is going to be from the other gas. Does that make sense? If you've got more of gas A, then more of the pressure is from gas A. So the air in our atmosphere is about 78% nitrogen, 21% oxygen, and 0.9% argon, and 0.04% carbon dioxide. So it's a pretty small percentage. And then there's a few other gases in there in even smaller amounts. So the nitrogen in the air exerts a pressure related to its fractional portion of the mixture. So 75% of the air is nitrogen, and so 78% is nitrogen, and so 78% of the total pressure of the air is from the nitrogen. The oxygen is 21% of the mixture, and it exerts 21% of the pressure. So here we have an illustration of a mixture of helium and neon. So the fractional composition, so if we have 80%, what color am I on here? If we have 80% neon, heliums, this is going to be a really long day. 80%, what does percent mean?
Part of 100.
Per 100, things per 100. So 80% equals 80 out of 100, which is 0.80. So this is the fractional composition, and this is the percent composition. So the fractional composition is just the percent divided by 100. So the partial pressure of the component is the fractional composition times the total pressure. So in this illustration, we have a total pressure of 1 atmosphere. 80% of the gas is neon, and so 0.8 helium. 0.8 times 1 atmosphere is equal to 0.0. yeah, 0.80 atmospheres. And I do actually have a stylus, which would work better. Are we sure it isn't Monday? It seems like Monday to me. So that's how they're getting these numbers here. So the total pressure was 1 atmosphere. The pressure from the helium is 0.8, and that is related to its percent composition of the mixture. The part of the partial pressure for neon is 20.2 because it's 20%. I'll go take speaking lessons and learn how to use English during the break. Any questions about that? I think we have a problem coming up here. An example. So say a gas mixture contains 64% methane, 36% ethane, and the total pressure is 1.44 atmosphere. What is the partial pressure of each component? Well, for the methane, it's 64% methane. So we convert that to a decimal, 0.64, and we multiply by the total pressure. I always forget to get my calculator out. So 0.64 times 1.44, 0.92. And for the ethane, okay. It's a very busy weekend. Birthday celebrations and all kinds of craziness. 36%, 0.36 times 1.44 atmospheres, which should give us 1.44. .52. Now, if we did this right, when we add these up, they should add up to 1.44, right? Because the parts have to add up to the whole, or it's wrong. Any questions? So, Dalton was another guy who studied gases. We have Dalton's law of partial pressures. So his law refers to mixtures of gases. And it's generally stated like this. Let's see if I can highlight that. The total pressure of a mixture of gases is equal to the sum of the pressures that each of the individual gases exert. So for air at 1 atmosphere, we learned earlier that it was 78% nitrogen. So then the nitrogen would be 0.78 atmospheres. Oxygen was 21%, and we calculated that, and it was 0.21 atmospheres. And the argon was 1%, so 0.01 for the argon, and those all add up to 1 atmosphere. And you may say, well, what about the other gases? Well, they're so small that they fall off where the significant figures are not important anymore. So they're in there, but there's such a small amount that they really don't matter at all. Mm-hmm.
Since we're having a rise in CO2,
Yes.
And so are we losing oxygen ratios to that? Because it's converting it from the carbon and absorbing oxygen?
Carbon dioxide levels are said to be rising, and so does that mean that our oxygen levels are going down?
Or like converting certain sections of it, because we're going to still have to reach one pressure. So something that has to be converted.
That's a good question. I don't know that the oxygen level, it's not that anything would be converted, but if the overall pressure is the same and one of the gases is going up, that just means that the relative percentage of the others is going down. But like it said, I think it was 0.04% was carbon dioxide, and the oxygen was 21%. So even if the carbon dioxide doubles, the change in the oxygen is going to be so small that we wouldn't even notice.
That section is still changing, but that tiny amount is still being...
Yeah, and those are averages, and of course you're gonna that's not the same everywhere. Like, we sit in this room and we all breathe and breathe and breathe, and we probably are causing the oxygen level to go down a little bit and the carbon dioxide level to go up a little bit. Then we open the doors or the fan comes on and it recirculates, and,
Where does the nitrogen come from in the atmosphere?
Where does the nitrogen come from?
Why is it a dominant element? Since we have so much hydrogen and oxygen.
Where did the oxygen come from?
From plants that convert to CO2?
But where did the CO2 come from?
From us breathing in oxygen and turning
But
into
where
this?
did we come from?
Oh, I don't know. I thought there was like something releasing it, like volcanoes. or
No,
something.
no, it's there.
Okay.
It's there.
Okay.
And that eventually goes back to where did existence
Okay,
come
okay.
from, and that's more of a philosophical
I
question.
There's so much. I wasn't sure if it was like something released by volcanoes or.
No, there's just, nitrogen is just a very inert gas, and it's just like the diluent, it's the thing that dilutes everything. We'll learn in a minute that, we need oxygen, and not enough oxygen is bad, but too much oxygen
Everything's flammable.
is also bad. Well, no, too much oxygen will actually kill you.
Oh, wow.
Oxygen toxicity.
Yeah, you can die.
That's why
Yeah.
if you breathe too much, you start getting dizzy. You can try it right now.
I can take video with this, that could be interesting.
We'll do it in
Hyper-
lab. We'll try to do our
hyperventilating,
lab
yeah.
experiments.
Okay.
Record.
Moving on, those are good questions. You guys ask great questions. Here's an example. A sample of hydrogen gas is mixed with water vapor. The mixture has a total pressure of 745 torr, and the water vapor has a partial pressure of, there's a word missing, 24 torr. What is the partial pressure of the hydrogen gas? Okay, these partial pressure questions and problems are actually very simple compared to the other gas law problems. So let's not make them too difficult. This is partial pressure. So Dalton's law of partial pressures tells us that the total pressure is equal to the partial pressures of each component. So we have what, hydrogen? So we have partial pressure of hydrogen, and we have water. So partial pressure of water. And so the partial pressures of the two components have to add up to the total pressure. Well, the total pressure is 745, right? Let's just rearrange this equation. We want the partial pressure of the hydrogen. So that's going to equal the total pressure, minus the partial pressure of the water. So 745 is the total. And the water was 24. So that would be what, 721? So that's the pressure of the hydrogen. Any questions? I used to wonder, to go scuba diving, you have to take all these classes and get certified and stuff. And it's like, what's the big deal? You're basically just swimming, right? It's actually a lot more complicated than that. Our lungs perform best at an oxygen partial pressure of 0.21 atmospheres, which is air, regular air at sea level. If we go up into the mountains, and I think hopefully most of you have been up to at least Kings Canyon or Sequoia Park once in your life, hopefully. You get up there, and if you run around or anything, you get out of breath faster, right? Because that's up around 7,000 feet or something. And the air, we say the air is thin, right? There's less air up there. The pressure of the air is less. And so, I think the book gave an example of hiking Mount Everest or something. When we get to a place less than a partial pressure, oops, pushed the wrong thing. Okay, partial pressure less than 0.1. And there's a nice typo. Atmospheres. There's a T missing. Good grief. T. There we go. It's a situation called hypoxia, which is not enough oxygen. You're going to feel the effects of lowered oxygen long before you get down to 0.1 atmospheres. But at 0.1 atmospheres, that's where you get into severe hypoxia, which can result in loss of consciousness and death, because you're essentially suffocating because your body cannot get enough oxygen to keep things going. So at higher elevations, the percent composition of the air is pretty much the same. It's still 21% oxygen, but the total pressure is less. And so the partial pressure of the oxygen is less. And when you breathe, you get less oxygen in, and your body complains about that. This is a little chart here that shows ranges of oxygen levels. So up here at 0, this is bad, and this is why when you fly in an airplane and they go way, way high up in the atmosphere where there's very little air, the cabin's pressurized so that we can all breathe, right? And breathe each other's germs and get sick. It's awesome. So this is what we're used to. More oxygen is okay up to a point, but when you get up too far, you get into oxygen toxicity. So that begins to happen above about 1.4 atmospheres. And symptoms of that include twitching, tunnel vision, and convulsions. Does that sound fun?
Yes.
Oh yeah, sounds great fun. That's pretty hard to do. Just, you're not going to do that by accident, in other words.
So when they give you oxygen,
Like if you're in the hospital and they give you oxygen, they're going to give you, they don't generally give you pure oxygen. It's going to be mixed with something, and they understand what levels would be good for you under certain circumstances. Yeah. They're going to look at the oxygen saturation of your blood, and if you don't have enough oxygen in your blood, that means that you need more oxygen. Now, if your lungs aren't functioning properly, then you may need more than 1.4 atmospheres of oxygen to help force the oxygen into your blood. My family had a close call with carbon monoxide poisoning when I was a kid, and ended up, going to the hospital and getting oxygen because your blood binds carbon monoxide preferentially to oxygen, and it doesn't want to give it up. And, well, the way you get it to give it up is by getting more oxygen in there. Yeah, so yeah, that was scary. But oxygen toxicity could happen when you're scuba diving, because when you're scuba diving, you're breathing pressurized air. Because as the farther you go down, the more pressure there is from the water on your body, and if the air isn't pressurized, you're not going to be able to inflate your lungs and breathe. And so the air that you're breathing through the tank has to be pressurized. Well, if you're breathing just regular air that's compressed at a higher atmospheric pressure, like if you're going 3 atmospheres of pressure, well, 0.21 times 3 is like 0.6 atmospheres of oxygen, right? So the deeper you go, the higher the pressure of the air and the more oxygen you're getting. Actually, that's, I think, from the nitrogen. Yeah. So, yeah, in this example here, I have a hard time seeing on here. So at the surface, 1 atmosphere of pressure, you're getting 0.78 atmospheres of nitrogen and 0.21 atmospheres of oxygen. If you go down 30 meters, now at 4 atmospheres, you're getting 3.12 atmospheres of nitrogen and 0.84 atmospheres of oxygen. And so the deeper you go, the more danger you have of getting oxygen toxicity. You're also getting an increased pressure of nitrogen. And there's something called nitrogen narcosis, which is also called rapture of the deep. And I don't scuba dive because that's just creepy to me. But they say it feels like you're drunk, like you're tipsy. And you can imagine that being, 50 meters underwater or so and feeling drunk and not being real sensible maybe was not a good thing. And people have died because they go down there and, if they're not trained and they don't have the proper equipment to go down that deep, then you can get in trouble because of the air that you're breathing. So when they go down below 50 meters, they use specialized mixtures of air. One of them is Heliox, which is a mixture of helium and oxygen. And so you can cut the concentration of the oxygen down so that you're not going to be, getting oxygen toxicity, but there's no nitrogen in there. The helium is going to make your voice sound funny.
Yeah.
Really, you can try that.
It's not really bad for you when you breathe in helium.
It's not bad for you as long as you don't breathe in too much. So, you've probably all at least seen people do this. You take a helium balloon and you inhale the helium from the balloon, and then you speak, and you've got this high little squeaky voice because you've got helium in your lungs and around your vocal cords, and it affects how they vibrate and the sound that comes out. So, it's kind of fun. So if you do that within reason, there's absolutely no harm to it. If you do that too much, though, in a short period of time, you could pass out because you're not getting any oxygen. Helium really isn't dangerous because it's lighter than air, and if you were to pass out, the helium is going to come out on its own, and hopefully somebody will kick you or something, you'll start breathing again. If you breathe in gases that are heavier, more dense than air, you can get into trouble because you breathe it in and it goes to the bottom of your lungs and it just sits there. And they have to actually tip you upside down to pour the heavy gas out, right? So, yeah, you need to be careful with these crazy things that you do. But taking a few inhalations of a helium balloon is not going to hurt you. So here's an example. A diver breathing Heliox with an oxygen composition of 5% wants to adjust the total pressure so that the partial pressure of oxygen is 0.21 atmospheres, that ideal quantity. What must the total pressure be? So how do we do this? Well, the partial pressure of the oxygen is going to equal the fractional composition times the total pressure, right? We don't really have, I think it's X of O2. We weren't introduced to a variable for that, times the total pressure. So we want to know what the total pressure is. The oxygen pressure is going to be 0.05, because that's 5% divided by 100. It's going to be 0.05 times the total pressure. So we did those calculations earlier where we knew what the total pressure was. So here what we need to do is just rearrange this equation and take the partial pressure of oxygen and divide it by the fractional composition. So the partial pressure that we want is 0.21 atmospheres. The fractional composition is 0.05. Oh, there it is. 0.21 divided by 0.05. So 4.2. And let's think about that. Does that make sense? Yes. It does. At regular air, at normal atmospheric pressure is 21% oxygen. 0.21 times 1 atmosphere is 0.21 atmospheres. Here, this mixture is only 5% oxygen. So to have the same partial pressure of oxygen, the total pressure of the gas must be higher. Any questions? This fractional composition, a calculation like this is good to know, but it's not essential. The kind we did before, we're adding up the pressures, or here's the total pressure and here's the partial pressure of one, what's the partial pressure of the other? That one's a lot more important. and here's why. One way to collect gas from an experiment is to collect it over water. This is what we did last Tuesday. We had a test tube. We had a test tube like this, and we had two substances in here that caused a gas to be released, and sometimes it caused sulfuric acid to be released because the hose got kinked up, and that was so exciting. But the gas is going to be pushed out of here, and then we run that underneath into a container originally full of water, and the gas displaces the water in the beaker or the test tube. So up here, we have the gas that we're interested in. Here it's hydrogen, I believe. But we also have a little bit of water vapor, because water evaporates, doesn't it? So here we have this space above water, and some of the water is going to evaporate and join the gas that we're interested in. So we've got hydrogen gas and water vapor. And so the total pressure in here is going to be equal to the partial pressure of the hydrogen plus the partial pressure of the water. We call that partial pressure of water vapor the vapor pressure of the water. That vapor pressure depends only on the temperature of the gas and the water. So if the water's warmer, do you think the vapor pressure is going to be higher or lower? It's going to be higher. Warm water evaporates faster than cold water, doesn't it? So the warmer the water, the higher the vapor pressure of the water in this space above. We can't measure directly in this mixture what that vapor pressure is, but if we know the temperature of the water, we can look it up in a table, like this one. So at 10 degrees Celsius, the vapor pressure of water is 9.2 millimeters of mercury, and as the temperature goes up, the vapor pressure of the water increases. At 80 degrees, it's 355.1 millimeters of mercury. And if we go up to 100 degrees Celsius, which is the boiling point of water, then the vapor pressure of the water is going to equal atmospheric pressure, or 760. So these are the sorts of problems we do need to be able to do. Hydrogen gas was collected over water. So anytime they say collected over water, you need to remember that there's water vapor, you've got a mixture situation. Collected over water at a total pressure of 758 millimeters of mercury and a temperature of 25 degrees Celsius. What's the partial pressure of the hydrogen? Well, we have a mixture here. We have the total pressure is the partial pressure of the hydrogen plus the partial pressure of the water, which we call the vapor pressure. So we did one like this before, but we were given the pressure of the water. So the partial pressure of the hydrogen is what we want, and that will be the total pressure minus the partial pressure or vapor pressure of water. We were given the total pressure of 758. And then we have to look up the vapor pressure of the water. So we look in this table and we find 25 degrees. At 25 degrees Celsius, we're going to have 23.8 millimeters of mercury of water vapor pressure. So, minus 23.8. $758 minus 23.8. So the calculator says 734.2. If we're going to think about significant figures, how should we report that answer? 734. Because we're subtracting here, and this number has uncertainty in the ones place. So we need to round our answer to the ones place. So our answer, I'll write it over here, 734 millimeters of mercury. And a calculation like this is the main reason we need to talk about partial pressures. Because when we do experiments in the lab, the most convenient way to collect the gas is over water. And then we have to subtract off the pressure of the water vapor so that we can look at the pressure of the gas that we're interested in. Any questions?